This video is going to be about time, length, and mass in relativity, and it turns out that all of these are relative concepts. What that means is that for someone that's moving in an inertial frame, so constant velocity, relative to us, their time, length, and mass measurements will differ from what we think our time, length, and mass measurements should be. So let's put Bob in a rocket ship and let's have him going at the speed of v, and v is not the speed of light, it's just some appreciable percentage of the speed of light, and let's figure out what's going to happen to him. First of all, we have the concept of time dilation. That means that clocks on Bob's ship appear to be moving slow according to us. Of course, the reverse is sort of true, that Bob looks at our clocks and he sees our clocks as running slow. But let's do an example with numbers. So let's plug in, let's say, first of all, let's get the time dilation equation here. So we have t is to over the square root of 1 minus v squared over c squared. And just to remind you what these different terms are, t is going to be the relativistic time, and then to over there is what we call the rest time. Okay, so the rest time right here, this is Bob's clock according to Bob. Bob's clock according to Bob, and for relativistic time, this is Bob's clock according to us. So we're both talking about Bob's clock. We're not really trying to compare Bob's clock with our clock. We're trying to compare what Bob sees on his clock, and we're going to look at Bob's clock and we're going to calculate how much time passes on Bob's clock as it's ticking slower, it's going past us. We can simplify this equation a little bit, so we can use this concept of gamma. So we can call this 1 over the square root of 1 minus v squared over c squared. We can simplify that and say t is to times gamma, and the gamma here is this term right there. The 1 over this term is the gamma, right? So that gamma factor comes up a lot. And so we can plug some numbers here, and just to pick out some numbers, let's say that v is 0.6 c, 60% of the speed of light, and then let's say that we watch Bob's clock and we watch, oh, I don't know, 10 minutes pass by on Bob's clock. I want to know how much time did we think that took. Oops, that's a question mark. How much time do we think that took? We see 10 minutes go by on Bob's clock, so we're looking at Bob's clock and it goes from here to there, 10 minutes pass by, and what do we think happens for that? So we just got to plug it in. For this equation, you can use any units for time you want right here. So you can use seconds, hours, minutes, years, whatever it goes. So let's scooch over here and do the calculation. We're looking for t, and we've got 10 minutes, and we have to do times 1 over the square root of 1 minus 0.6c squared over c squared. Now, as long as you keep things in terms of c, then it's always going to work out great. So this is 10 minutes times 1 over the square root of 1 minus 0.36, right? This is going to work out well because 1 minus 0.36 is 0.64, and I can take the square root of 0.64 as 0.8, or just do it on your calculator. So we get 10 minutes times 1 over 0.8, and 10 minutes times 1 over 0.8, well, 0.8 is 4/5, so this is going to be 5/4. So we'll get 5/4 of 10 minutes. That's going to be 10 minutes times 1.2, so that'll give us 12 minutes, right? And so we're going to watch Bob's clock, and it's going to be ticking more slowly. So we're looking at Bob's clock, and it's going from, say, the 12 up here to the 2. That's 10 minutes, right? Yeah, that's the minute hand. And instead of that taking 10 minutes to happen, it's actually going to take 12 minutes to happen. Now, of course, for Bob, according to his perspective, his clock just takes 10 minutes to go 10 minutes. That's all. But from our perspective, it takes actually 12 minutes for that clock to go 10 minutes, right? I want to point out this factor right here, this gamma factor 1.2, because we're just going to use that in these other ones when we talk about length, when we talk about mass, right? So just remember that gamma for this particular speed of 0.6c, gamma turns out to be 1.2. So we can just keep that. Good. Let's go to a different page and let's talk about length. So another relative concept happens to be length, and that means that lengths that Bob measures are going to be different than lengths that we measure. So let's get Bob back in his spaceship again. Okay, let's say that Bob is holding on to a meter stick in his spaceship. That's a meter stick. Okay, now it turns out that length is a relative concept, and it's really actually space that's a relative concept. The amount of space that the meter stick takes up varies depending on who you ask, as long as you're talking to somebody in an inertial reference frame. So remember, this is non-accelerated. So what are we going to do here? Well, first let's get the length. This is called length contraction. So that's the concept. What it means is that we're going to measure length on Bob's ship as actually shorter than what they are in a rest frame of reference. So if Bob's holding on a meter stick, he thinks it's a meter long, and we're going to measure his meter stick as actually less than a meter. And the length contraction equation says L is LO divided by gamma. Right? And once again, LO, that's the rest length, and then L is the relativistic length. Right? Let's just do the same example from the same speed as before. So we'll just say V is 0.6 c, 60% of the speed of light, and let's have LO be 1 meter, and we're going to calculate what is L. Well, really easy, because we already know what gamma is, so we can say L is 1 meter divided by gamma. We know gamma because we already did it on the other page, so that's 1 meter divided by 1.2. 1.2 is 5/4, so flip that over and it's 4/5, so we're going to get 0.8 meters. What that means is that if we were to measure Bob's meter stick, it would actually be shorter. It would be 0.8 meters. And the faster he goes, the shorter it gets, right? Another relative concept is actually mass. And so we get this law of mass increase. Bob's mass, according to us, is going to be more than his rest mass. And the equation, once again, involves gamma. So we just have m equals mo times gamma. Same equation, same gamma. So if we were to measure Bob's mass, it would have increase in the same amount that his time increased. And so using the same, this is rest mass. Let's write this out, rest mass and relativistic mass. Right, rest mass and relativistic mass. So same V equals 0.6 c, and let's say that Bob's rest mass, just to make it really easy, is 100 kilograms. Let's find his relativistic mass. We already know the formula right here, so it's going to be m is 100 kilograms times gamma. We know that gamma was 1.2, so his mass is going to be 120 kilograms. So that is, according to us, his mass increased. His mass is 120 kilograms, and his length decreased, right? So these are the three things: mass increase, length contraction, and time dilation.